maximum number of points bumped down was like a B, low B. So, but I do want to go through problem number 1, the rolling without slipping problem, because that's an important thing. Okay, so the problem says this is at 30 degrees. And you have a disc rolling down the incline. It has a mass of 1 kilogram and a radius of 0.2 meters. What's the acceleration of the center of the disc? Hey, that's what I got. Okay, so free body diagram. Sure.
If we're following your steps.
Yep, let's follow my steps. Okay, so 1, no fixed point. And then since the about point is the center, the moment of inertia is 1/2 1/2 times the mass times the radius squared. So that is 0.02 kilogram meters squared. And then the free body diagram. The weight acting down is 1 kilogram times 9.81. And then there's a normal force. And then there's a friction force. The friction is what makes it rotate. If there's no friction, it would just slide down the ramp. And the friction force is, so if there was no friction, this point would just be sliding down the ramp. So in order to keep that at 0 velocity, the friction force has to act that way. And I'll use a coordinate system that's lined up with the ramp like this. Then rho, force, moment. About point is the center. So for the weight force, you have, it's at the center, there's no rho vector. The force vector is, this angle here is 240 degrees. Well, this angle is 30 degrees. To go from the positive x-axis to that is 240. So it's 9.81 times cosine and sine of 240, which is, I think, negative 4.905, and then like negative 8.5. Okay. And cross product is 0. Then for the normal force, the rho vector is 0, negative 0.2. Force vector is 0n. So the cross product is 0. And then for the friction force, the rho vector is 0, negative 0.2. The force vector is positive FF 0. And so the cross product is positive 0.2 FF. There's no fixed point, so we have to use Newton's second law. So that says negative 4.905, negative 8.50 plus 0n plus force of friction 0 is equal to the mass of 1 times, what do we know about the acceleration of the center of mass? It's in the negative x direction. And actually, we do know that, but overall, as a general approach, we're just going to assume that it's parallel to the x-axis. We'll just call it a0, and we're going to get a negative value out for that. Solving for the normal doesn't help us at all in this problem. So, yes, sometimes it's fun. So, yeah, just do it for fun. But because this is serious, I'm only going to do the x. So, force of friction minus a is equal to 4.905. Okay, so that's our first equation. And then the moment equation says 0.2 FF is equal to the moment of inertia 0.02 times the angular acceleration. And so that gives us our second equation that says, let's multiply by 5, and we get the FF minus 0.1 alpha is equal to 0. So now we have two equations with three variables. So we need one constraint equation, and that comes from, okay, so we have three variables, only two equations. So we need one more equation. Uh, 1/2 times the mass times the radius squared, so 0.02. One-fourth is if it's rotating like a paddle. Let me rescore yours. I'm just kidding. Mm-hmm. Right. Mm-hmm. So it's, I think you're right, I did. Yeah. That's right. Yep. No, just. Right, the quiz. Okay, so the equation we need is for rolling without slipping. And that says that, I've given that with a couple of different forms. But if you use that rotated coordinate system, you always know that the acceleration is equal to, how did I write this? Negative, so 0, 0, negative alpha crossed with 0, negative R 0. Or this, or A is equal to negative alpha R. I think this is the way I wrote it. Ignore this stuff. Yes, because if you think about, yeah, the negative you can put that anywhere in the, multiplication is commutative, so you can call it a negative R, negative alpha, whatever, as long as you have that negative sign. Mhm. Oh, well, you need to switch the R value from that. There needs to be an extra negative in there. And you can just see it from thinking about the motion. Yeah, so here are the two, so here are the two possibilities. If this is alpha, then this is the acceleration of the center of mass. And if this is alpha, this is the acceleration of the center of mass. So either way, this is a positive alpha in the z direction and negative acceleration in the x direction. And this is a negative alpha and a positive acceleration. So either way, the sign is switched. Okay. That's what I
mentioned that too. You did a quick note. You said just make sure these are opposite.
In class. Oh, during the test, right?
You put the vector. Well, you didn't even do that.
That's right. Just the magnitudes, yeah.
I actually assumed that since I
yeah.
That it was going to
work. Right. Okay. Yeah, that's a pretty minor, problem with this. But yeah, just remember that you can figure out the direction relationships by just imagining what's happening, and in both cases, the signs are switched. Okay, so our last equation is, I can write it as A plus 0.2 alpha is equal to 0. And now we have three equations for three variables. And we can solve it. And I think what you get is that the acceleration, well, the way I have this drawn, we know that the acceleration has to be in the negative x direction. And the math comes out to tell you that A is equal to negative 3.270. Any questions about that? All right. So we're going to do like two more example problems. I think I'll do one and then I'll have you do one together. I don't know if we'll get through it today. But we'll do these two more example problems with rotating coordinate systems, and then we'll move on to the last topic, which is not the last topic, by the way, that's in D2L. I still have to change that. So in D2L, it says that the last topic we're going to do is three-dimensional rigid body kinetics. Instead, we're going to do vibrations, mechanical vibrations. That's right. It's, if you're interested, or I would guess most people are somewhere between not interested and moderately interested. You could just skim through the notes, that are on D2L You don't have to sweat the details too much, but it sort of give you an idea of how it works. I think 3D kinetics is a really interesting topic because in almost every kind of physics, going from 2D to 3D is not that big a deal. Rigid body kinetics, there's a drastic change in the approach going from 2D to 3D. And so it's kind of interesting. Want to know why it is?
Sure.
Okay. Yes. Okay, so
But before that, why
I think because I don't think 3D rigid body kinetics is going to come up in your other classes in a way that you need it, and vibrations will. So I think it'll just serve you better going on. Yeah. Okay, so before we go into this, so the reason for the big difference is in 2D, so imagine this is a rigid body in 2D at instant 1. Say that's the axis of rotation. And then at instant 2, it's at this position. That's supposed to be the same rigid body. It looks a little different. So at instant 1 and instant 2, it's changed positions, but its axis of rotation in both cases is parallel to the z-axis. And the mass moment of inertia of this object about the z-axis positioned here is still the same as the mass moment of inertia positioned this way. Okay? This rotation about the z-axis didn't change the mass moment of inertia about the z-axis. Okay, but if a thing, so I'll write it as I sub z is the same at both instants. And so because of that, well, you can think of so the rotational Newton's second law, what it really says is that the sum of the moments around the about point is equal to the rate of change of the angular velocity. Yeah, capital H. We haven't talked about it that way because if you take the time derivative of the the angular velocity, no, the angular momentum here, H, is the mass moment of inertia in general, it would be a matrix, times the angular velocity. And if you take the time derivative of that, if the mass moment of inertia stays the same, you get this times the time derivative of the angular velocity, which is the angular acceleration, and that's the way we do it. Okay, so this form comes from the fact that the time derivative of the mass moment of inertia is 0. Okay, otherwise you'd have to use the product rule there. Yeah, so H is the angular momentum, and it's defined as the mass moment of inertia times the angular velocity. Under squiggle means that in general this is a matrix. When we do 2D problems, we can treat it like it's a scalar, but in 3D problems it's a matrix. Okay, so if you do it in 2D, what happens when you take the time derivative of I omega, generally speaking, is you have to use the product rule, so you have I dot times omega plus I times omega dot, which is alpha. If the time derivative of I is 0, then you just end up with this. And that's why in 2D, we just use this form that says add up all the moments about around your about point. It's equal to I alpha. Okay. But now look at what happens in 3D. So if you start out with an object like this, and then you rotate it into a position like, let's say, this, because you can now rotate in about any axis or any combination of axes. Okay. And you think of the coordinate system like this, say. Now, Ix at instant 1 is not equal to Ix at instant 2. And so because of that, it's true of any of those, because that's sort of a combined rotation. But the idea is that you have elements of this matrix of mass moments of inertia that change in time. And therefore, the time derivative of the angular momentum is not equal to the mass moment of inertia times alpha. And that brings up all this stuff. Instead, it's equal to well, you don't solve it this way, but it's equal to this times omega plus this times alpha. And so the way you have to go about it is you have to do your calculation in a coordinate system where the mass moment of inertia does stay constant, because we don't have any way to deal with this time derivative of the, okay. And so that's not hard to find. It's easy to come up with a coordinate system where the mass moment of inertia stays the same as time goes by. Just choose a coordinate system that rotates with that body. But then what you have to do is use our approach for rotating coordinate systems, And so to take that time derivative, what you get for, H A dot then is equal to, it's equal to I alpha plus omega crossed with I omega.
That's supposed to be high value.
Yes.
So would a sphere kind of like
Yep, that's exactly right. Yep. Yes, that's right. So a sphere, you don't have to worry about it. That's the one, or anything that's rotating, I suppose, about an axis of symmetry, I think, is the same way. Okay, that's the idea. I said I talked about that too much. But it's sort of cool how, in sort of like a watching a train wreck kind of way, it's sort of cool to see how this seemingly minor issue just derails everything that we're used to doing, you know? Yes. In practice, though, you start doing 3D kinetics, you're probably going to use energy methods to do it in the long run. If you take another dynamics class, the next one you take will be based on energy methods, and it makes three-dimensional problems a little easier to deal with. So things get complicated using a Newtonian approach for rigid body motion in 3D, but you don't tend to use a Newtonian approach anyways. And vibrations are going to come up in, you know, several times in your next couple classes. So we'll talk about that a little. Okay. So here's another example. Let's say we have a disk rotating around a pin. Okay. And that pin is rotating around a hinge that's connected to the ground. Let's say that this is moving at 5 radians per second. And relative to that, this disk is rotating at 10 radians per second. Both of those angular velocities are a constant. Let's say that the disk radius is 0.6 meters. And if the point that we're interested in is down there, oh, I have to give the length of that too, but we're trying to find the acceleration of that point P. Okay, so let's say that the length of this arm is 1 meter. And this angle is 45 degrees. So which of these two bodies is the horse? Yeah, and
So is the disk fixed to the long pole?
it rotates around the long pole.
So is that shaft?
It's like a
The shaft's not rotating. This is rotating around that shaft.
Well, the shaft.
This is also rotating like this.
Shaft is.
So this bar, like if you stood over here, that bar would hit you as it came by. But in addition to that, the disc is rotating around the bar. Yeah, so it would slice you as it hit you, possibly before, but you wouldn't feel it hit you. It's not really going very fast. It would be a minor nuisance. I don't want you to be too concerned about that. It's going just over 1 revolution per second. Okay, so there are 2 rotations. There's this one and the disk. The axis of rotation of the disk depends on where this is in its rotation. Okay, so that means that this is the horse and that's the cowboy. And now we have to choose, so we know that the coordinate system is going to rotate with, let me number these. So I'm going to call this body 1 and this body 2. So we know that the coordinate system is going to rotate with body 1. Now we have to choose an orientation for the coordinate system and a location for the origin. Might as well choose an orientation that goes like this. Well, then this one's just rotating about the x-axis. Yeah, well,
Just postponing the step, isn't it? It doesn't matter what the angle of the coordinate system is, because we're going to have to deal with it once we deal with it.
you can give your final answer in whatever coordinate system you want. So we could do it this way and give our final answer in this coordinate system. But although, now that I think about it, either way, you have to deal with one that's not perpendicular. If we choose a coordinate system like this, that body is rotating around that, but this one's rotating. So maybe let's just use a standard one. But
Would it be easier to do like polar coordinates that works?
no. We want to think of this as one rotation riding the other rotation, and use the rotating coordinate system. And then there's maybe 2 choices of origin location, 2 good choices. One is here, okay, and the other one is here. If we put it here, is the origin accelerating? No, so that's good. If we put it here, is the origin accelerating? Okay, so we could do it that way. We get the same answer, but probably the simpler choice is to put the origin here. So I'm going to, well, because it would be fine either way. Neither one is better than the other one. But if we tilted it 45 degrees, then we just have to, now the rotation of this one is an x component only, and that's good. But the rotation of this one is between the x and y axes. Either way, we're going to have to deal with one that's not aligned with a coordinate axis. So if we choose one like this, the horse, body 1, is rotating around our y-axis, and this one's rotating around a tilted axis. Okay, so the coordinate system is, let's do it like this. And we know that the acceleration of that point P is equal to the observed acceleration of P Yes. Yep.
Oh, that would make mine boring.
You could derive it though.
With no scratch paper.
Times.
Yeah. And
No, they don't give it to me.
They ask for
yeah, they do.
They don't give it to me. I have to go in and ask for it.
Oh.
Oh, yeah.
Okay.
But I'm like, I don't want to get up and move and like get paper. I'm gonna put it all on this.
Okay. Okay. So we got the observed acceleration plus the time derivative of the angular velocity of the coordinate system crossed with the position vector plus 2 times the angular velocity of the coordinate system crossed with the observed acceleration, observed velocity of p plus big omega cross quantity big omega cross p. Okay, so let's start filling in these values. So first, let's do the observed velocity and acceleration. When we talk about the observed velocity and acceleration, the way to think about that is this motion keeps happening, but we'll imagine that this rotation isn't happening. So all we have is a circular motion of p happening out there at a distance. Okay, so the observed velocity of p is equal to omega cross r. And what's omega? So it has a magnitude of 10 radians per second. And so we're going to do that as a magnitude times a unit vector. What's the direction of the unit vector? Yep, cosine and sine of 45 degrees and then 0z. So this omega is positive 10 times 0.7071, 0.7071, 0. And we're crossing that with the r vector. We should have rotated the coordinate system. Well, it's not so bad. What's the r vector for that circular motion? The magnitude's 0.6. So, yeah, negative 45. Because the vector we want is from here to here. So the r vector is 6 times cosine of negative 45 degrees, 0.6 times sine of negative 45, 0. And so that is, you can pull out all the scalars. So we have 6 times 0.7071, 0.7071, 0, crossed with 0.7071, negative 0.7071, 0. Those two unit vectors are perpendicular to each other. So we can just use the right-hand rule to figure it out. I mean, you could plug that into your calculator too. But we're crossing a unit vector in this direction with a unit vector in that direction. So that's in the negative z direction. So this is equal to 0, 0, negative 6. Any questions about that? And Now the observed acceleration is alpha cross r plus omega cross quantity omega cross r. We don't have any alpha. So this is omega is 10 times 0.7071, 0.7071, 0. And we're crossing that with omega cross r, which we already have, is 0, 0, negative 6. Yeah. So now we're doing the acceleration, but this omega cross r is what we calculated up there. Right. Okay, so what do we get here? So this is 60 times negative 0.7071. And then positive 0.7071, and then 0. I pulled out the 6 there, yeah. But then I still need to get a number for that. Can someone multiply those for me? I guess just multiply one of them. What is it? 42.4, positive 42.40. Yeah, 42.4. Plus or minus 4.4. That's round off error. Okay, what else do we need? What are we doing? We're going through all the things that we need for this rotating coordinate system equation. What's capital omega? Zero, negative 50. Because the right-hand rule says it's in the negative y direction. 0, negative 50. That's capital omega dot. 0. The position vector, yeah. So the position vector is all the way from the origin to here, right? So that's going to be 1 times cosine and sine of 45 plus 0.6 times cosine and sine of negative 45. It would have been a little easier. You're right. I forgot about those radii. Next. Oh, I did? Oh, I was smarter then. Okay, so this is going to be 1 times cosine and sine of 45 degrees plus 0.6 times cosine and sine of negative 45 degrees Can someone calculate a number for that? $1.13, okay. .283. Okay. So there's the position vector. And now we have everything we need. So the acceleration of P is equal to the observed acceleration, which is negative 42.4, positive 42.40. Plus capital omega dot cross P, and that goes away. Plus 2 times capital omega, which we know, 0, negative 5, 0, crossed with the observed velocity, which is 0, 0, negative 6, plus 0, negative 5, 0, crossed with the quantity 0, negative 5, 0, cross P, which is 1.13, 0.2830. Okay, so, let's stop there, but I'll calculate those numbers, and we'll come back on Friday. I'll have the numbers for that, and then we'll go through it with a rotated coordinate system and make sure we can get those two to match. Okay?